So we're still working with electrochemistry, and I don't know, I'm really partial to electrochemistry. It just seems so clean to me. And there's so much chemistry here, and it's so applicable. For example, how do you stop rust? Can you stop rust? Right? From the table, it's directly from it, iron solid goes to iron plus 2, right? Is that oxidation or reduction? Right? Fe solid's going to oxidation state 0, going to plus 2. Right? It's getting oxidized, it's getting more positive. Another way I can tell is that it's oxidized is it's producing electrons, right? So it's losing E negative, so it's got to become more positive. And then if you want an oxidation reduction to occur, well, heck, you can add it to a reduction reaction. And if you add them up and they come up to be positive or negative, you know what'll happen. Which one was it? What was that equation? All right? I think they had a cell or something. So that E cell needs to be what? And you're going to have spontaneous reactions. E cell would be positive. Right. So that's the power of this thing. This is going to happen, and there's nothing you can do to stop it. Right? You can figure out what the overall reaction is going to be. You have to multiply the top one through by 2, right, to get those electrons to cancel. And then write your overall reaction. But you end up with an overall E0 of, Jessica, what would I end up with? 0.84. All right, she saw the trick. You don't multiply E0s by the number. All right, very good. If I had a candy, I'd throw it out there. Okay, 0.84 volts. Great. So that's all rust is. Iron solid dissolving, going to iron plus 2. Okay. You can't stop it. But you can replace it with something else, right? Replace this oxidation reaction with something that's more reactive. And this is what's really curious to me about electrochemistry. Even though you've got the iron there, the other one's going to react up first. So you just find something, another metal, that's more reactive than iron. So in other words, something with its E0 that's more positive or negative? More positive. And man, you're set. So you go up here into the table. Now, where the heck is iron solid? Here it is. I think that's the half reaction we're at. Okay. And again, these tables are always reduction or oxidation tables. They're always reduction. So the electrons are always on the reactant side. Things are getting reduced, right? So iron plus 2 going to Fe solid. So I'm talking about Fe solid going to Fe plus 2. So I'm imagining that reaction getting flipped, right? Iron solid is the reactant getting converted to Fe plus 2. So that means my little sign here gets flipped to a positive. And that's what it said. Okay. So what metal could I use instead of iron solid? Aluminum is really cheap, right? Where's aluminum? Aluminum's not really cheap, but it's plentiful. Where the heck is aluminum? You see aluminum? It's way up here somewhere. I saw it. 1.66. Oh, am I on the screen here? Oh, sorry. Way down here. Okay. So you flip it, it becomes a positive 1.66. Sounds great. However, you're going to have water reacting first, so you can't really pick these guys. So these are so reactive. And plus, what's the funky thing about aluminum? Does aluminum conduct electricity? It's a metal, right? So you should say yes. But, man, I have no qualms at all. Sitting there in a bathtub, Jose's got his knife or whatever, and I don't know, or plug it into the cord, right? Right? So he's got the electricity. They're holding the cord. He's going to hand it to me. I just have a piece of aluminum, touch it to there. I'm not worried at all. What's going on with aluminum? Get an aluminum can. Try to get it to conduct. aluminum is so reactive, it reacts with oxygen. There's a layer of aluminum oxide outside of all aluminum. It doesn't conduct. So you have to scratch it off really fast, right, before oxygen reacts again to get a surface that's conductive. Or really screw it in tight so that you can actually tear underneath the surface. And see what I mean? Aluminum's not so great. But anyway, so you can't go below water reacting. So you only have a couple choices here. You can't go up because like cadmium, lead, and these guys, they're going to be positive, but they're going to be smaller than iron. So iron would react first. You've only got a couple choices. In this table, you can either work with chromium or zinc. Well, those little nails, remember, they were what coated? Zinc coated. So there's coming from, right? Because it's a positive 0.76. The zinc all reacts, then it just steps down. Then the iron, whatever else is there. Okay. So it's kind of neat. Describing voltaic cells with line diagrams. So instead of just having these things occur naturally, let's separate out into physically separate these guys out, the oxidation reduction reaction, so that those electrons don't just combine by having the reactants physically touch. Let's have those electrons pass through a wire or something, right? Make a electronics. Yes?
What we were just talking about, is that the same thing we use for like nickel chrome wire?
Nichrome?
Yeah.
Nichrome is it's a metal, but it has a very high resistivity. So you can just run a little bit of current through there, and it just heats up like a Nickens. So that's not electrochemistry. That's just high resistant metal, and you're passing a voltage across it. For bomb calorimeter, usually they have some reaction going on, right? And then you.
In order to put it across the thing. So after what you just said, I was like, oh, that kind of makes sense. Because we always put the length of the wire in, measure before and after, because that wire is going to blow with the reaction.
Yeah, I'm not sure which reaction they're doing. But so if you measure, with nichrome wire or any metal that's resistant, if you can you know the amount of current that passes through it, you know the amount of heat, so that's maybe where they're coming from. Describing voltaic cells with line diagrams. I think you're going to like this. Iron reacts spontaneously with copper 2. Obtain the half reactions for this reaction. Okay, well, I'd just write everybody iron solid, going to Eustacio, going to its half reaction. It's going to Fe plus 2. And I could finish it. 2 electrons. Copper plus 2. Everybody, it's going to what, Daisy? Copper solid. Right? Put the 2 electrons over here. Right? Okay. What is the standard electrochemical cell potential for this reaction? Standard, so that means I'm getting it from the chart. So we got to find iron solid. Oh, I already circled that one. Iron solid has to be on the reactant side, so I have to flip it. That's a positive 0.44. And now I need copper plus 2. It's a reduction reaction. Copper plus 2 has to be on the reactant side. Here's copper plus 2 plus 1 electron. Oh, here's copper plus 2 plus 2 electrons, right? Positive 0.34. Okay. So the standard electrochemical cell potential would be 0.7 feet. Right? That'd be my, I guess the notation should be E0 cell or something, right? One thing that's curious that's coming up in the homework is it looks ugly. They're going to say, okay, they're not even going to give you the reaction. They're going to ask you what it is, but they're going to tell you that you have these things present. And they say, hey, what's the reaction? Does a reaction occur? They give you a whole bunch of ions. So pretty much what you do is you just pick out the half reactions involved, and you know the half reactions that add up to be positive E0 cell. When you have a reduction and oxidation half reaction, it'll happen. So that's how we'll solve something like, I think it was at the very end. Where was that? Here. See, doesn't that look odd? Where's this even coming from? they give you a solution of all these ions. They say, hey, write a reaction. So it's pretty much what we just did. You're going to look in the table of reduction potentials and find the half reactions instead of being given the reaction like we were. Right? We were given the reaction. Yep. Oh, because I have to. Okay. So how did I know how to write this? Well, this one, luckily, our homework is so much easier than general chemistry. But let's review the whole rules for general chemistry anyway, because then you see how I did what I did. First, you balance. Let's erase it, right? Because we copy it. We start out right here, right? Write what the compound is on the reactant side. Write what it is on the product side, and then you balance everything but O and H. Well, ions are done. Then you balance O by adding, anybody remember? H2O. So, but no oxygens, thank goodness, right? Then you balance H by adding H pluses. No hydrogens, we're good, right? Then you balance the charge by adding E negatives to the most positive side. So iron solid has a charge of 0. Iron plus 2 has a charge of 2. So that's definitely the most positive side. I have to add E negatives to it. And then how many? 2. Now that's a lot longer answer than you wanted, Javier, but that's all that crap is, all that stuff is going through my mind when I'm doing this. Okay. Write the line diagram. Okay. So it's, well, we have the overall reaction right here. The line diagram isn't so bad. Okay. Pretty much. Oh, but we need to know what's the double bar in a line diagram. Oh, wrote it up too high. What's the double bar?
Salt bridge.
Salt bridge. This little guy right there, right? Because you can't just have the 2 beakers of the stuff. You have to complete the circuit. You have to make a circle, right? You have the wire coming out to the voltmeter, coming back into the other hunk of metal. But you need something to connect them. That's that salt bridge. And that's that double line. Okay, completes the circuit. Okay, so anode, cathode, let's see. What's getting oxidized? What's getting oxidized here? Is it the iron solid or the copper plus 2? Or hold on, it's the cathodes first. No, yeah, that's right. The anode's on the side. The iron solid's getting oxidized, right? So pretty much we just write the 2 compounds. And if you know what the concentration is, we would write it next to it. Okay. If they said it's 0.2 molar iron plus 2, we would write 0.2 molar iron plus 2 here. And we have either a comma or a solid line separates the 2. Do you know when you use which one? If there's a phase change, like liquid to solid, solid to aqueous, whatever, then you draw the solid line. So this would be a solid line, not a comma. Okay. And then then also this is the anode. It's the cathode. What's a good way to remember anode is oxidation? It's the only way I remember this. I hate memorizing stuff. They both start with a. It's the only way I remember this. Anode, oxidation, both start with a vowel. Everyone's got their own way to remember this. That's how I remember it. I don't know if that helps you or not. But anode oxidation. Okay, anode oxidation. Cathode reduction. So then what's going on with the cathode? Copper plus 2 going to copper solid. So copper plus 2 going to copper solid. If they would have told us the concentration of the copper plus 2, we would have write it in there. And I draw a solid line or a comma here. Solid line. Yeah, phase change. See, told you it's not so bad. Okay. We use a comma when if copper plus 2, copper plus 1, right? They're both the same phase is a comma. Both the same phase is a comma. Okay. Non-standard conditions. So that's the line diagram. So it's kind of easy to go from a line diagram to the reaction, pretty much just replace what's in the center with an arrow, right? You know what's going to what? Non-standard conditions. Sochi, what does it mean to be non-standard conditions? Yeah, you can throw off the 25 degrees, but they're not going to throw off the 25 degrees. They're going to keep it at, they're going to keep the 25 degrees part, but they're going to screw up the what? Or they could screw up the pressure, or they could screw up the, more than likely, the concentration, right? It's supposed to be what molar? 1. So let's just make it 0.5. All of a sudden, non-standard conditions. Okay? So there's, most common is just to change, oh, here. I would do it, maybe make it this way. The concentration is not equal to 1. That's the most common. Something's off. Under non-standard conditions, E cell must be calculated using the Nernst equation below. How are numerical values found for each term in this equation? Okay, Victoria, here's our Nernst equation. Now let me ask you, Victoria, which one of these, or which variable here is read on the stinking voltmeter in the first place? E cell. E cell is our voltmeter. With what units, everybody? Volts, good. Okay, that's where you get E cell. It's going to be measured, or I guess you can calculate it using Nernst. You can predict it. Zach, where's this E0 cell coming from?
Original equation.
Yeah, the original equation. Pretty much something like this, right? You'd have to write them out. Cathode reaction, the anode reaction, add up the E0 cells, and we'll get it. Okay? From the table. How about the little n? Destiny. How about the little n? I'm just catching up here. It's the moles of electrons that end up what? In here. They end up, what's that, Javier? Canceling out. All right, it's the number of moles of electrons that are canceling out to get this E0 cell in the first place. Okay? In that case, it would be 2. So we got that one. This Q. We've seen Q before. And we had a fancy name for it, Brandy. It was called reaction. Ooh, good. Reaction quotient. What did we use it for? You fly so fast in these classes, I think we forget what the heck we use it for.
Concentrations outside of equilibrium.
Yeah, you use it to see if you're at equilibrium or not. If the concentrations are outside of equilibrium, right? So you plug everything in. Concentrations of products over reactants. And if it's at equilibrium, you'll get what? What do we call it? The K, which is called the equilibrium constant, right? Concentration of products over reactants. And if it's at equilibrium, you'll get this number, whatever the reaction is, right? Okay, so you're outside, like Brad said, of the equilibrium concentrations. Something's off. It could be 1, it could be all of them. Well, you're not going to get K anymore. You get Q, right? That's all it was, is does Q equal K? Is Q bigger than K? Is Q smaller than K? And you know, which direction is the reaction going to shift? That's the game that we were playing. So since you don't know if you're at equilibrium or not, you put in a Q. Now, if you are at equilibrium, though, the measurement on the voltmeter will become what, Daisy? You leave this set. You leave this setup set for a nice long time. This number right here, it slowly goes which way? Slowly goes down, right? Until it finally reaches 0. And now we're at equilibrium. Okay? 0 volts. Make sense? So those batteries are dead when they're at equilibrium. There's no more work they can do. Okay, they're in there.
Always out of equilibrium until they run zero.
Yeah, and then they're at equilibrium. Okay, So let's rearrange our Nernst equation then. If we're at equilibrium, right away, E0 cell is 0. Okay? That has to equal E0 cell. Sorry, E cell is 0, right? Because that's the guy in the voltmeter. And if I'm at equilibrium, I don't write Q anymore. I write K. There we go. This is how we're going to get equilibrium constants from E0 cell. Right? We have to do some algebra to get it, but it's right there. Right? E0 cell is going to equal 0.0592 over n. Another equation to worry about. Okay? That's how we can get equilibrium constants from our standard reduction potential tables. For any reaction, right? Any redox reaction. And what was n again? The moles of electrons that cancel out when you added up those two half reactions. Okay. A Voltaic cell has an iron rod and 0.3 molar iron 3 chloride and a zinc rod and 0.2 molar zinc sulfate. The half cells are connected by a salt bridge. Write the notation describing the cell. Write the notation describing the cell. Yeah. Yeah. Now make sure the anode's on this side. Okay. So you might want to figure out just what the heck. What the heck the reaction is in the first place. That's how I have to do it. I have to figure out what the reaction is first. And they want, look at the further question down. They want you to predict the cell potential anyway. So it might be easier to do B first, because then you know what the reaction is going to be, and then you do A. I think it'd be easier to do that first. Because since you got to find out what the reaction is anyway, so you can write the line diagram. So how would you go about this? Jose, how are you going to figure out what one of these half reactions are? Iron chloride. Okay. Now iron 3 chloride. I'm just focused on this iron 3 chloride since he picked it out. If you go back to this table, is there any iron 3 chloride in here? No. But what is? Iron 3. That's what you're interested in. Who gives a doohickey about the chloride? Now, you could care about the chloride because chlorine going to chloride is in here. But that means you had better have something to do with chlorine gas. But it doesn't. It's just talking about the iron rod and the iron 3 chloride. So all you're really interested in is finding the half reaction that involves those two. Right? Look at the other solution, the other cell. See what two they're interested in there. Write that half reaction. One of those, and then you add up those two half reactions, so you get the most, what E0 cell? The most positive. That's the game. That's the rules of the game. Figure out what those two half reactions are, find them in the table, and add them up so you get the most positive E0 cell. And it's going to happen if it's positive. Okay? So the zinc rod would mean I'd be messing with zinc solid. Zinc sulfate solution means I'm messing with, yeah, but zinc with what charge? A 2, right? Now that's the only charge zinc has. But I know it's +2 because I know sulfate is a -2. Remember sulfate? Oh, don't tell me this died on me again. This has a -2. That means he has to have a +2. Okay. So find these two half reactions. Let's see, let's go back. You find one of them? So I don't have to dig in here. Zinc going to zinc plus 2. Okay, here's zinc going to zinc plus 2 is a negative. So there's this half reaction. And then the other one was, what was it? How could I forget that already? Oh, it was the iron plus 3, right? Okay, now where the heck was that? Do you see iron plus 3?
Does it matter if it's like aqueous?
Well, ions have to be aqueous. Yeah, all ions have to be aqueous. You said it's at the top? Here's an iron plus 3, but it's going to iron plus 2, so that one won't work, right?
We also have an iron plus 2 to iron 0, but there is none that's iron 3 to iron 0.
We don't have iron 3? Maybe I made...
Not in this chart.
Really?
Yes.
Well, let's erase one of these ones then. Or miss, because you have to have iron 3. It's got to be in that chart. Well, I'll just, iron 2, someone found it, so let's just work with it. Iron, we had that marked already once, didn't we? Yeah, right here. Okay, so let's circle them. The zinc and the iron. So you believe me so far? Which one of these are you going to flip? You have to flip one of them, because notice how the electrons are on the same side for both. You definitely flip the zinc, right? Excellent. Why? How do I know? Because I can, if I flip the zinc, I have a positive 0.76. Add that to a negative 0.44, I have a positive number. If I flip the negative 0.44, add it to negative points, I have a negative, then it's not going to work. So you want to get E0 cell, so you get the most positive. Not just positive, it has to be the most positive. So, I forgot what I said. We said flip the zinc, right?
Yes.
So, zinc solid goes to zinc plus 2. And that was 0.76 volts. And then we had iron plus 2 electrons goes to iron solid. And that was negative 0.44 volts? Okay. But now we don't need to write the entire reaction because we're just after this cell notation thing, right? And this gives you enough to write it. Because in the cell notation doesn't have anything with stoichiometric coefficients. If you did have to multiply through by something, it doesn't. No, it's not there. So where is my anode? Where's my anode half reaction? Which one is that one, Mariella? Which one's my anode half reaction? Yeah, the zinc. Oxidation. Remember anode oxidation. So I'm going to write zinc solid, a line. Did they tell us the concentration of stuff? They did, didn't they? Zinc solid, and it's 0.2. So 0.2 molar zinc. And you can write zinc sulfate if you'd like. ZnSO4. Sulfate's not doing anything, though, so I just left it out. Cathode, iron plus 2, and its solution is 0.3 molar. Iron solid. Okay? So there's my line diagram, my cell notation. Line diagram. Predict the cell potential. Okay. Predict the cell potential. Monica, how are we going to do that? I was just going to add these two up, and I thought we could go on. But what's wrong with that? What if I add these two up? What do I get? What is it, 0.32 you said? This is what mathematical variable? What symbol is this? E0 cell. The question is predict the cell potential. What's the mathematical symbol for cell potential? Right, Andrew's on. E cell. Is E cell the same as E0 cell? No. We have that equation. E cell equals E0 cell minus 0.0592 over n or something, right? So we have to actually calculate it. Yeah?
When you balance out the equations, would you need to put the number in the equation on top, on A? Because you're going to multiply to cancel out the other terms.
Well, no, here I don't, because there's 2 is going to cancel out really nice. I think that's why I made the question to be 3, because then they're actually multiplying through. But let's say you did have to multiply. Here you don't. But let's say you did. So then you end up with having like 3 irons or something. No. It's just the reactant. Right? And what it turns into. You don't put the stoichiometric coefficients in. Nope. Nope. And I think it would be really confusing if you did, because someone would say, is that a stoichiometric coefficient or is that a concentration? So they don't do it. Okay. We'll just write Q. Okay, we got to fill this in. So my E cell, you already told me what E0 cell was, positive 0.32 volts, minus 0.0592 all over 2. Yeah, because we changed it to iron 2 chloride, so. Products over reactants. What would that be? Right? Can you see it without writing the overall reaction? Right? Products over reactants. So the products are just zinc plus 2 in a solid. So all you're interested in is zinc plus 2 as a product. And its concentration was 0.2. Is it squared or anything? We can write it in. Is it squared or anything? It's just 1, right? If it was 2 zincs, then you'd have to square it, right? Or 3, you'd have to cube it. Just like before, writing products over reactants raised to their stoichiometric coefficients. The reactants are zinc solid and iron plus 2. Yeah, excellent. So 0.3 is on the bottom. And we're not squaring it or anything because it's just iron plus 2. Okay, and that's how you get your answer. What units do you put on that answer, Jamie? Units? V. Very good. So whatever you get, volts. How about predict a value for the equilibrium constant for the overall cell reaction? So Naya, how are we going to do that? How do we get the equilibrium constant? We have the nice reaction up here. How do we get its equilibrium constant? Right? The only way that I know of, right? Because you have to wait till E cell goes to 0. And when it does, you're at equilibrium, and then this equation's valid. E0 cell is 0.0592 all over n log of k. And what's my E0 cell again? 0.32. Nothing's changed. That's the table. That's never going to change on you. Now this one I think you might want to do on the calculator to make sure everyone's getting it right. Yes. So I'm going to, I guess I could put in 2 there. I didn't put in 2. multiply 0.32 times 2, divide it by 0.0592, raise it to the what power? 10. Excellent. 0.32 times 2. Did you get a huge number? Yeah. Should it be huge? I bet you we got a nice big positive number for E cell. E0 cell is nice and big and positive. This is something that's really going to occur naturally. There's going to be a lot of product on this reaction. So it should be a huge number. Take 0.32 times 2 divided by 0.0592. Then you have to raise it to the 10 power.
For my volts, I only got a 0.005 increase. So my E cell was only 0.35.
So, right? Oh, way up here. I haven't done that one. Yeah, that could very well be close to equilibrium. I don't know. I just picked those numbers. So you get about 0.325 or so for the top one? Yeah. Oh, all I'm saying is this E0 cell is a nice big positive number. So at equilibrium, there's going to be a lot of product because this is a very spontaneous reaction. Okay. Yeah. Yeah. Because look at our table. Yeah. It's very positive. Okay. Calculate the E0, delta G0, and K for the following reaction. Okay. So what would be the game plan for this? We're not going to do it, but just figure out what the half reactions are. Exactly. Figure out what the half reactions are. So if the overall reaction is this, figure out what they are. You're going to have electrons on one side, electrons on the other. See what the E0s are. Right? So you add up those E0s, and that's how we're going to get E0 cell. Right? And remember, delta G is minus NFE. So delta G0 will be minus NFE0. So once you know what E0 is, you got delta G0 then. Right? Just because of this. And then K, well, we've kind of already found out how to use K, how to get K. Right here, you use this equation. So not bad. Here we have pretty much just look at all of your reactants, right? Everything that's there, and try to write a reaction, right? You'd have to pick out the half reactions involving cesium 3 and cesium 4 and manganese 2 and manganese and permanganate. Find out those two half reactions, add them up so that you get the most positive E0, and you'll have the overall reaction. Okay. So give that stuff a shot and come by. I'll be glad to help you out.